Welcome to this video. This is the last part of video tutorial where I will show you how to perform a 3D simulation of designed propeller in OpenFOAM, open source CFD tool. So in process of simulation we will find the power consumption of the propeller, and we will find thrust, axial thrust of propeller. This is the main performance characteristics of propellers. Okay, so I have prepared the case example which you can use for fast CFD simulation. You can change the geometry, for example, and repeat the simulation with different geometries. Okay, so you can download this example case on GitHub. Just in search line, paste and find my repository. This. Let's try to find it. Let's go here. Let's go here and go to the repositories. And here you will find the OpenFOAM Propeller Simple Foam case. We will be using the Simple Foam solver. This is a steady state CFD solver. And here you can see the two folders. This folder for propeller and this folder for stator. If you saw the previous video tutorial where we have created the meshes of internal and external domain, we will use these meshes for CFD simulation. So let's just download this OpenFOAM example cases, download like zip file, and here just let's paste this zip archive to empty folder, and let's extract this. Click OK, and I will use it and paste it to this folder and delete this last folders. Okay, so we will be use these two cases for running of simulation, and go to the mesh files. In previous video tutorial we have created the UNV files. These files of meshes of two different domains, this internal mesh of propeller and external of a water around a propeller. So let's copy these two meshes and let's paste it where we have the rotor and stator, and let's just paste the internal mesh to rotor to this folder and external to stator. Okay, so now we have to, in constant folder, we have to create the poly mesh. This is a native format of OpenFOAM meshes. We can convert this UNV file to native OpenFOAM format. For this, let's go to OpenFOAM. You can install it and find the installation tutorials in YouTube also. Okay, I recommend the Joseph Nagy, author of different basic OpenFOAM video tutorials. And let's go to path to where we have our case with rotor and stator folder. Here I paste the command LC, and it show us folders where of the path where we are. And let's go change directory, command paste it, and go to rota directory. And let's see our internal mesh here and different folders of OpenFOAM case. And here let's convert the mesh. You need IDS UNV to form command, and let's paste the name of mesh here. You can use the tab key button on keyboard. If you paste here I and click tab, you will paste the full name of mesh and click enter. And now we have the converted mesh, and you can to check the quality of a mesh which we have. You can use the native OpenFOAM command for this. It's this command called check mesh. Paste it and paste enter. And how can you see? We have the mesh OK. If we have some troubles with mesh, we will see the some falses here without mesh OK. That means that our mesh is enough for CFD simulation in general cases. Okay, so let's go to Stata. Click LC and let's convert the mesh IDS UNV to form and choose the external mesh with tab button and press enter. After that, let's check mesh again for Stata domain, and we have the mesh OK here also. Okay, when we have this that it working, we have the converted meshes. We have to merge these two meshes to one simulation case. We'll be using the master case like Stata. We will be working in Stata folder. Let's go to Stata. Here we will be working, and rota we just merge with Stata domain, and we will get all our mesh in one folder of Stata. To do the merge of meshes, we have to use this command merge meshes, and if you will just paste help but with one on this character, you will get some description of this command. How can you see? We have the merge meshes command, the usage example, and we have the two options, master case and add case. Here we have to paste this data and add case. This case means what case we want to add of mesh from this case to this master case. After that, let's just paste here the merge meshes and Stata and rota case. Press enter. And you will get here the some polymesh here, but we merge these cases with one folder. We can to just use this polymesh and paste it here, but we can to delete this, and I will show you another way how you can to automatically merge the meshes and save it, overwrite it to constant folder of mesh directory. Let's go here, rotostata, and open the OpenFOAM, and for merge meshes we have to use this command overwrite. Okay, let's press it. We add to previous command overwrite, and let's press the check mesh but we have to go to stata case ls, and here in stata case we don't get the one folder, we have this polymesh, it a full mesh here, because it's the size of the mesh is 30 megabytes. Okay, after that let's go to OpenFOAM, click LC, and press the check mesh, and here we can see that our merged mesh is okay. After that we can also to open and check the mesh in Paraview. For this, let's create one empty file which we can use in Paraview for automatically open the OpenFOAM case form.foam. This file is empty. Close all. Okay. And after that, let's open the Paraview. This is open source CFD post processor. It's a very powerful tool. I recommend you to download it. And let's wait some time. And we have opened it, Paraview, and let's go to OpenFOAM starter case, and let's open the foam.foam folder file. And if you will click apply, you can see our full domains here. And let's make a clip operation and change the position of this slice clip. And how can you see, we have the full domain, and if you will activate the surface with edges and activate the crinkle clip, you can see that we have the merge meshes. This first domain, external cylinder, and internal cylinder with propeller here. Okay, it means that this merge meshes is correct. Let's go to OpenFOAM. Let's paste command clear here, and after that we have to create another command. We have to create the interface between internal and external domain. Let's go to polymesh, to the boundary, open it, and here you can see inlet, outlet, external, ME2, ME1, and wall patches. But we have to change the patches. For ME, we will be using the ME cyclic interface for ME1 and for ME2, and for wall we will be using the wall name. For external will be just a water. We will be using here a patch like inlet, and for outlet boundaries also. Okay, here we have to paste cyclic ME, and we have to add the connection between these two ME interfaces. I prepare some example how looks this command. Let's go to OpenFOAM Propeller and OpenFOAM Backup, boundary, polymesh, boundary, open it, and just to let's see how looks this boundaries. Here we have to paste this type of boundary, cyclic ME. I just copy it, paste it here, paste it here also, and let's copy this, no, ordering transform, and just delete the some tabs, and neighbor patch, it means the connection between this link to this interface here. And let's copy this and paste it for this interface also. And we have to link this ME1 with ME2. It means that we have to set here is 2 ME2 with this ME connection. Okay, it looks correct here. And for external outlet and inlet we have a patch, and for wall we have a wall. This wall a propeller surface. Okay, so let's close this boundaries files and go to see the domain starter. We set up this boundary. Let's go to system, and here we have the toposet dict file. We have to create the ME interface between patches and tell OpenFOAM about this interface. Okay, create the some source set of this interface. Okay, let's go to OpenFOAM, and here you have to set only one command, toposet. Press enter, and you will create the ME interface between these two surfaces. For example, if you have the several interfaces, in your case, in another OpenFOAM cases, you have to just copy this, paste it, for example, to this file here, and change the names. Okay, I will return this file in initial state, and let's close this file. We have complete setup of interface and merge meshes, and let's go to setup of this initial conditions and boundary conditions for simulation. Let's go to velocity file. I will show you how look the velocity file. We have for inlet, we have inlet outlet, for outlet inlet outlet, inlet outlet. This boundary means that we don't have the fixed value of inlet of velocity. We have velocity is defined by propeller working. It means that if a propeller require much mass flow, it boundary returns the mass flow which will transport from across our propeller. And for external cylinder, we have in any surface we have inlet outlet conditions. And for propeller wall we have the no slip. It means that on surface we have the 0 value of velocity, and for ME we have the cyclic ME interface. Here in this line we have the ME and ME2. It means that we just to write this to one line. We can to merge also here this all surfaces. It will be looking like if we will use this inlet, for example, paste it. After that let's use the outlet and external, and after that we can to delete this, and it will be correct also for OpenFOAM, because we have a similar type of boundaries with values here. Okay, let's save the velocity file. Let's go to pressure file, and here we have the very simple setup. we have the zero conditions for all boundaries, and we have the cyclic EMI for EMI1, EMI2 interfaces surfaces. Here, let's close the UP and go to omega. For omega, we have the inlet outlet. It means that not important which value we have in internal fields, and for this the very important is what we using here. This we will define the type of wall function for model turbulence model. Here we have the smooth surface, but we can we use the wall function, just wall function for omega value. If we have the y plus for tetrahedral mesh, for example, without boundary layers, with a very rough mesh on surfaces, we have to use the wall function for to get the right velocity profile. Okay, let's use this omega wall function here. Let's close it and let's go to the newt. In the newt, for wall, for propeller, we can to set the rough wall. If we will paste here the 0, you will get something like smooth surface of propeller. But I have used this microns value in meters here, value of ruggedness of surface on propeller. And also we have to set for inlet, outlet and external the calculate type of boundary and cyclic EMI in all fields. Okay, let's go to K. Here we have also inlet outlet condition. It means that we don't fix the value of K, and you can set here, I think, almost any value of K for simulation. And we also have to use the wall functions for turbulence energy. And let's go to the epsilon. We don't use the epsilon because we have the K omega SST turbulence model. If you want to use the K epsilon turbulence model, you have to set up this epsilon file also, and it's almost equal, have almost similar types of boundaries like in omega, but here we have epsilon wall function for propeller surface, and we have the cyclic EMI again. This file was created automatically, just to show us where we have the rotor domain, and show us where we have the rotor domain, and we have to recreate this file, and we have to create here the region of rotor, because we will have the multiple reference frame approach for simulation of rotation of our domain of propeller. So after that, when we have these right boundaries here, let's create the rotation domain. And for this we have to use some native function of OpenFOAM. Let's clear it. We have to create the cell region of a rotor. It's internal domain with propeller. For this we have to use a command. It's called like set command, and in set command we can to create some sets of our cells or interfaces or another things for OpenFOAM. So let's set the help, and here we have to create the cell zone for rotor case, for rotor domain. If you will go to cell sets, here we have the region 0 and region 1. For region 0 is a master case, is it is data external, because how can you see the external cylinder has a much less number of cells. It's you can to check which domain you have here, just to check the size of number of cells here. The region 1 is a rotor domain, which you have to use for rotation. So let's use this cell zone set command. Let's paste it here, cell zone set command. We have to paste the new name, rotor new, and set to cell zone command, and here we have to set the region 1, because we have the region 1 here for our internal cylinder. Also, you can press enter, and now we can see that creation of our sets of rotor was performed successfully. If you will go to constant polymesh sets, you will get this rotor sets here. You will open it and you will get the number of cells here. It's similar with this case also. Okay, it looks correctly. And for this rotor domain, we have to use the multiple reference frame properties. Open it in here, and we use the cell zone. It's called rotor, and set this active. Yes. Here we have the non-rotating patches. It will be the EMI patches, EMI interfaces. For axis we will be using the 0 or 0 0 1. 1 means that rotation axis we have z direction, and value of rotation speed will be this value. It means that we have the 3000 RPM, rotation per minute. Okay, let's save it. After, let's go to transport properties. Here you have to set the Newtonian. We have the Newtonian liquid, and new it will be value of kinematic viscosity of water, because we have a hydraulic propeller. Let's go to turbulence property. We have here the omega SST, and we have to activate turbulence. But if you want to deactivate turbulence model, you can to use here the off and off command. It will increase the stability of simulation. If you want to increase the stability, if you get the crash in simulation, you can try to off the turbulence model. perform some several iterations of simulation and activate again the Omega SST here. Press on turbulence here. Okay, let's close it and let's go to system directory. And this file we don't use for this case, but you can use it. In my previous video tutorial about simulation, CFD simulation of impeller, you can to see what does mean this file here. And let's go to control dict file. Here we set the start time is 0, is the first iteration, and in time we have 1000 iterations in our simulation. And we want to write every 100 iteration the results, and we want to save only one write interval simulation. If you want to save more, you can paste here the 5 previous steps or 2 previous steps, but I set 1. It save disk space on your hard drive. Okay, here is important thing. It's we want to calculate the y plus function. It means that if y plus is very high, it means that we have some troubles with defining of friction losses in our simulation. You have to have this value not more than y plus, have to be less than 300. Okay, it's a very rough, of course, but it work for engineering applications, for Propeller, for example, because if you will get something like 2 or 100, you will get something like similar for engineering point of view. But if you working in science and you want to validate simulation or another purpose, you have to your criteria for y plus will be less than 5, maybe for 1 for cases with Omega SST turbulence model. But in general, in engineering application, you can to use y plus smaller than 300 in average on your surfaces, of course. And we write interval have almost like we have similar, like we have the right interval for all our simulation. And also important thing, we calculate the forces. The force means that if you will save the forces, you will save the turkey or moment, or also it's called moment, on your patch wall. This is a propeller wall, a propeller surface, and you can calculate the force. It means if you will divide it by gravity constant, you will get the thrust. I will press here the force divided force is z, because we have the axis, rotation axis is z. Here we have to divide by g, is gravity constant. You will get a thrust in kilograms. For example, I will set it here like kilograms. Okay. So, and we want to save each iteration. We will be using the P and U, and because we have the liquid of water, we set the 1000 kilogram per meter power 3. Here it's the density of water, and center of rotation we have the 0, 0, 0 in different direction of axes. Okay, let's close this control dict file, and here we have the decompose par dict. And the important things here that we want to perform the parallel simulation on your CPU. On my CPU, if I will go to description of my CPU, with number of cores, I have this Ryzen, and I have the 12 number of physical cores here, and I want to parallel my simulation to 12 physical cores. I set here the 12, and here I want to define how I want to split my geometry in different directions. I want to split the two direction in X and Y direction, and for Z direction I want to split it 3 times. And it means that if you will multiply this 3 coefficient, you have to get this value, number of subdomains. It means that 2 multiplied by 2, it will be 4, and 4 multiplied by 3, we will get the 12 here value. Okay, so another thing, it's not so a matter, so it's not so important here, and you of course can use the different methods for decomposition, and you will go to documentation or OpenFOAM if you is this interesting thing for you, and I just to hide it. And let's go to FreeCAD schemes. Here I use the linear upwind grid view, and how if you remember which schemes we have used in impeller simulation of pump, I have used also similar settings of divergence schemes here. It's a good choice for tetrahedral meshes, and when you perform simulation of hydraulic pumps, hydraulic turbines, wind turbines with tetrahedral mesh, of course, and another thing like turbo machineries with incompressible liquids and high Reynolds number. Okay, with turbulent type of flow. Okay, here I have the similar settings of schemes like with impeller, and let's go to FreeCAD solution file. Here I have the similar solvers for P, GAMC solver, smooth solver. You can try to GAMC for U, for example, and you will get something like similar. Something similar like with these settings. For this case, it's not so don't give you some advantages if you will change these settings. Maybe you will get some speed up for convergence of simulation, maybe. Okay, or you will get some instability of simulation or more stability. Okay, here we have the non-orthogonal correctors. I use the 3 non-orthogonal correctors for tetrahedral meshes without boundary layers, maybe with. If you will check mesh with OK, you can see that you get. Sorry, we have to write from here and just LC command, and let's paste the check mesh again. And how can you see, we have the very much big non-orthogonality, maximum value of orthogonality, because we have used tetrahedral constructed mesh with a very difficult shape of geometry, and it's a very big deal to create the very high quality mesh for very difficult shapes. You can use the hexahedral mesh, for example, if you have the AutoGrid or TurboGrid of ANSYS software, but also you can try to split your geometry to blocks in Salom and create the hexahedral mesh there also. Okay, let's set the 3 here, and these two lines we have to use because in file 0 and file for pressure we don't have the some fixed value of pressure in our domains. For all boundaries we have the 0 gradient value, but internal field value means that this just initialization of field in 0 iteration. But we have to fix for simulation of some value of pressure in our domain. We can choose any cell. If you paste it, for example, you have the 3 million cells, you can use this cell or one cell, it doesn't important. Let's paste here the 0 cell and let's paste some fixed value of pressure. This pressure is Pascal divided by density. This is just in OpenFOAM native format of this solver, simple form, and we have to use this notation here. And here we have set these relaxation factors. For tetrahedral mesh and for very high stability, I have this coefficient for relaxation factor. You can try to increase, for example, this relaxation factor. The maximum value for relaxation factor will be 1 for all fields. But for this relaxation factor, I think you will get the very high instability of simulation and maybe crash, because your mesh is not ideal, because it is a bad mesh in point of view tetrahedral mesh, because it's tetrahedral mesh, and we have to use some relaxation factors. It will reduce the speed of simulation if you will reduce these relaxation factors, but it will increase the stability of simulation. So it means that if you have some instability in your simulation, you can try to reduce this coefficient, for example, for pressure 0.2, for U 0.4, 4, and 4, for example. But you can also use, for example, this coefficient also. It's a very empirical factor for your simulation. But in my general cases with tetrahedral mesh in turbomachineries, these settings work in general case, and simulation is fast and very stability. Okay, I think it's enough for running of simulation. And let's go to the OpenFOAM. Let's paste here the clear command and just let's prepare the simulation. Just we have to use the decompose par, and it will create the some part of our meshes for paralleling simulation. And after that we have to use the command of mpi run minus np. We have to use the number of cores in your decompose pardict file, and after that we have to choose the solver. Here we use the simple form, is a steady state simulation of incompressible fluids, and minus and parallel. Okay, and after that let's press enter, and we have run our simulation here. How can you see? The simulation is fast, and let's wait some time, because the first save of results will be in 100 simulation. And let's go to post-processing, and let's go to forces, for example, and here you can find the thrust. Let's show us a forces. Here you have the total force. It's force from pressure of fluid, and this force from friction of velocity on your surface. Okay, we have to use the total force on that direction, because we have this direction, that direction of rotation, our propeller. And here we have the negative value of meaning this negative value, the mean of, we have the force which we get the direction here. And how can you see? We have got something like 1020 newtons. If you will divide it by gravity constant, you will get in kilograms your thrust here. Also, you can to see value of your thrust in your log of simulation. How can you see? Here you can see the sum of forces is this value. It corresponds of this, and sum of moments. It also total moment. It's a turkey on your shaft of propeller. It means if you want to find the power consumption, you have to multiply this total moment multiply by your rotation speed in radian per second, and you will get 12 kilowatts power consumption of this propeller. Let's wait simulation, because how can you see the force, the thrust of is changed with iterations, because we have some high value of these residuals for pressure and for velocities here. Let's continue simulation, and how can you see we have some smaller values, and in some time of simulation you will get some constant value of your value of thrust and value of power consumption. You can also to open the moment that, and you will get the turkey on your propeller shaft. Let's go to here, and here you can also use this value or from file. Okay, let's close it and let's wait some time. How can you see our case is conversion not very fast? We have this value. I think we will stop simulation using the Ctrl+C case on your keyboard. Press this, click here, but I don't want to clear. I just want to use these values for save the parameters of our propeller. Okay, let's try to open our case in Paraview. Let's delete this and delete this, and let's try open the form point form again. Let's here, if we have this results of simulation in parallel simulation folders. If you want, you can to merge these meshes, results of your simulation. You can to just paste here command reconstruct par, and here ck latest for latest time. It means that it will be used this last, because if you have, for example, several save times, it will save all these to these results, but I use the latest time tag, and you will get this 500 results of your fields to one file. Of course, you can to open the different type of cases. You can to open the decomposed case in parallel mode or reconstructed case. It's want to use this one file of Paraview. Okay, let's choose a decomposed case, for example, and here we have the different fields. You can to see how it looks, and after that let's I will show you how to create the streamlines of the flow around your propeller. For this, let's open 2 times of our case, because for the first case we will be visualize our propeller, and for second case we will visualize a streamline. For this, let's use the internal mesh, and for form here the second, we want to create the stream tracer. If you click apply, you will get something not understandable. So if you want to get something informative streamlines, you have to change here the seed type. Let's choose the point cloud, click apply, and how can you see here we have something understandable. If you will want to, for example, you can change 1.1, maybe some bigger value of this you'll get here, or I think we can use the radius have to be equal to your propeller. Okay, and after that let's just increase the number of points for your field. And how can you see? If you will activate, for example, this velocity value visualization, and for example let's hide the sphere, and for this you can to use this visualization of pressure, and you will get the some small value of pressure on your section side, and on pressure side you will get the high value of pressure. It means that this difference of pressure, you will get this mass flow from your external part and to the flow will be from your section side to your pressure side. flow direction. Okay, so you can change some visualizations here. For example, let's go here and let's try to some render. I want to change the background, for example, and I want to enable the render. You will get something very big radius of your streamlines. You will to decrease it. Maybe you want to increase this specular, and let's decrease the line width. But we have to decrease the line width for stream tracer. Let's choose it and let's paste here 0.1 or 0. This value. This increases the specular, and of course you can to paste, for example, number of sample per pixel. It will increase the quality of your rendering here. If you will decrease this, you will get only the geometry if you activate it, and we can also activate the shadows. It will increase realistic of your visualization here. And let's to reduce number of your number of points. For example, return it to default. And you will get something like this not informative case. Of course, you can use some tricks for visualization. I will show you. For example, let's just increase the number of points to 1000, and let's deactivate ray tracer, and let's to clip this. Okay, let's clip the streamlines. Apply, or you can to invert. If you will hide the flow, you will get something like your propeller with streamlines. If you want to, for example, to clip this external, you can use another clip. Use the cylinder, and let's change the direction of cylinder in right direction of that direction, and let's set the center to 0, and let's reduce the radius to, for example, like you have for your propeller. Let's hide the cylinder, and you will get something more informative. And for this clip, let's use this rotation. You have the U and velocity is magnitude. Okay, and after that you can activate the enable ray tracing, and you will get more interesting visualization of your simulation, I think. For example, your propeller with visualization, and we can to decrease, for example, your line width. For example, 1.2. Maybe use this with render as tubes. So let's use the specular. Maybe we will increase it to this value, and it looks more interesting here, I think. And we also to, for example, change this rescale your value, for example 0.6. Okay, and for this also you can to change color map. Change it here also. For example, it will be X-ray, this or this. Let's set the some default jet, and if you will increase the thickness of lines, you will get something more informative. Okay, let's increase this to for example. Okay, and now we have our visualization of your field with rendering. Thank you for watching, subscribe to the channel, goodbye.